Let me introduce Sebastian Velazquez, who is going to talk about moduli space of Lie algebras and foliations.
Aí, tá bem? Well, thanks to the organizers for giving me the opportunity to give this talk. Today I will talk indeed about moduli spaces of Lie algebras and foliations. The point of this talk is to describe some moduli spaces of foliations, its geometry around points which correspond to foliations which are induced by Lie group actions, right? So we will do that in the following way. We will construct a space parametrizing Lie algebras of vector fields on some variety x. And we will define a morphism from the space to the space of foliations, taking each algebra to its induced foliation, right? The foliation induced by this Lie algebra of vector fields. So, well, this is useful in the sense that we know a lot about quite some stuff about the formation theory of finite dimensional subalgebras. So if we can prove under which circumstances this is an isomorphism locally around some points, then we can translate the things we know from the formation theory of finite dimensional Lie algebras to the formation theory of foliations. So let us start. So in this talk, a foliation will be an exact sequence like that. So the term on the right is called the normal sheaf of the foliation, and its rank is the codimension of the foliation. And the term on the left is a tangent sheaf of the foliation. And we will require it to be close under the Lie bracket of vector fields when we view it as a subsheaf of the tangent sheaf, right? Well, the singular scheme of a foliation is just a singular scheme of its normal sheaf, and away from this singular points, right, which are the singular scheme is supported at the points where the normal sheaf fails to be locally free. So away from these points, we have a regular foliations, just like Joao just explained, right? So a few examples. If we have a smooth map, or more generally a dominant rational map, we can easily construct a foliation whose leaves, as Joao just explained, are the connected components of the fibers of this map, right? And the codimension will be equal to the dimension of the codomain. And another example in which we will particularly insert in today, just as I explained, will be foliations which are induced by Lie group actions, right? In this case, the leaves will be the orbits of maximal dimension of the action, supposing G is connected. So if we have a connected subgroup of the automorphism group of our X, I think I forgot to say X is smooth projective over the complex numbers. So if we have such a subgroup, we can recover the tangent shift of the foliation in the following way. We can look at its Lie algebra G as an algebra of global vector fields on X. And we can just look at the subsheaf of the tangent sheaf, which is generated by these elements, right? So this is the tangent sheaf to the foliation of this action. Yeah, we can take it as a definition. So these foliations are important to me for two things. First, they have some, say, good geometric properties, which are often have to do with the properties of the Lie algebra, which is nice. And the other thing is that they are very important for studying moduli spaces of foliations, right? In the literature, there are many results showing that some families where every member is a foliation of this type is stable, meaning that this family fills out an irreducible component of the space of foliations, right? One of these works, which was particularly motivating for me, is this one due to Jorge Vittorio Pereira and Fernando Kuckerman. And among other things, there they show the following. So take X to be the projective space, and take a Lie subalgebra whose exponential acts with trivial stabilizers in codimension 1, right? So in this case, we can define a morphism from a space of subalgebras of global vector fields to a space of foliations, whatever these spaces are for the moment, taking each subalgebra into its induced foliation. What they prove is that if this foliation has, say, reasonable singularities where this depends, depending on its codimension, this is something different, then this morphism here is an isomorphism locally around these points of G and f of G. So to me, the natural question was, okay, what happens if the stabilizers are not trivial, so we have more general action, or X is not the projective space, right? So this is the question I address in this work. And now let us be more specific about what these spaces are. So we defined what a foliation is, and we will define these spaces in terms of the deformation functors they represent, right? So a family of foliations will be just over some base S, will be the relative version of what I said a foliation was. We just take the same definition, and we change the tangent sheaf of X for the relative tangent sheaf for the projection from X times S to S, right? Well, the codimension is indeed the rank of the normal sheaf of the family. And we require the tangent sheaf of the family to be closed now under the Lie bracket of relative vector fields, right? Okay, so the family will be called a flat family if the normal sheaf is flat over the base, right? So we can define a functor taking each base S into the sets of flat families over this base, right, for a fixed X. If you know a thing or two about the Quoos scheme, then you'll realize that this is a subfunctor of the Quoos functor of the tangent sheaf, right? So it is no surprise that by a theorem of Federico Qualbrum, this functor is represented by a closed-up scheme of the Quoos scheme. And this will be today our model space of foliations, right? Just to word the space, for instance, Alan described another space, and in many occasions we can compare this space with the one Alan presented. So we have this model space of foliations, and now let us move to the algebras, right? So again, we fix a base S, and we take, just for have a nice notation, L to be the algebra of global vector fields on X. So we can define what the trivial deformation of L over S is. It's just the shiftification of L, but equipped with a O-linear Lie bracket, right? We extend scalars and extend the Lie bracket too. So now a family of subalgebras, say of dimension D, will be a locally free subsheaf of this sheaf of rank D, which is closed under this new Lie bracket, right? And again, we can define an analogous functor, yeah? And again, you should notice, or maybe after some time you should notice, that this is a subfunctor of the Grassmannian functor of D-dimensional planes, linear spaces in L. So it's more or less the same proof of the one as the one from Qualbrum, but this functor is also represented by a closed subscheme just now of the Grassmannian, right? So now we have our two spaces, right? The space of subalgebras and the space of foliations, and we would like to connect them, but keeping in mind our motivation, which was explained before in the work of Jorge and Fernando, and we would like to take every Lie algebra G into its associated foliation, right? We hope, maybe, we can construct a morphism like this, a morphism of schemes like this, okay? So by the universality of this moduli space, all this, will be equivalent to having a tautological family of foliations over the space of subalgebras, right? Because a morphism like this is equivalent to having a family of foliations, and if we require it to be this morphism here, then over each algebra we must have the foliation induced by this algebra, right? So, well, we do that. I mean, being this space of subalgebras, we have a universal family of subalgebras. And just as we defined what the foliation induced by a subalgebra was, we can do the same for families. We can define what the family of foliations induced by a family of subalgebras. We do exactly the same, right? So we construct this tautological family. And if this would be indeed a morphism, then by the universality of the space here, this family should be flat, right? Because morphisms are equivalent to flat families of foliations, which is what this space represents, the functor this space represents. But unfortunately, this is not the case. This family is not flat at all. It's quite easy to construct weird examples of things that are clearly not flat. So what do we do? I mean, we should do something. And what can you do if you have a function which you really, really want to be continuous, but it is not, right? Well, I mean, one thing, the obvious thing, which actually works, is you change the topology of the domain, right? So that it is now continuous. Or maybe just paraphrasing that, you partition your domain into pieces such that your function is now continuous in each of these pieces, right? So in algebraic, this setting, what I just said is you take the flattening stratification of this space associated to the normal sheaf, right? Because now continuous means that the normal sheaf is flat. So we partition the whole space such that now the normal sheaf is flat. So now, over each piece, we have a flat family, right? So if we have a flat family, we get over, for each piece, we have a morphism like this. And I mean, obviously, then we have a morphism from the stratification to the space of foliations, right? And this is the only thing that works. In some cases, it would be that this stratification is trivial, but this is the only thing that works. If we require the morphism to be this one, right? Like, okay. So now things like this. So the question was, what happens with this assignment when we have more general stabilizers or more general varieties? And the main theorem today is the following. If we are standing here at a subalgebra satisfying these two cohomological properties here, which are properties of the tangent sheaf of the induced foliation, then this morphism here is an isomorphism locally around these points, right? So the question is, well, essentially the same answer as before, right? But we changed the hypothesis on the singularities by the hypothesis on some cohomological, for some cohomological hypothesis. As a corollary, one thing I didn't say, but of course, the automorphism group of X acts on this space, and also acts on this space. And it's quite easy to see that this function here is equivariant with respect to these actions, right? So in particular, if we're staying at a rigid foliation, we get a rigid Lie algebra, we get a rigid foliation, which is nice because we can construct then many irreducible components of the spaces of foliations, right? Because they're rigid. As a corollary, for instance, semi-simple subalgebras are known to be rigid. So if we have a semi-simple subalgebra satisfying this hypothesis, we get a rigid foliation. And now you could ask, well, how about this hypothesis? How good are they, right? Well, say in the case of the motivational paper, where the stabilizers were trivial, then in this case, this hypotheses are okay if we require the structure sheaf of the space to have 0 first cohomology, right? Because then the tangent sheaf of the foliation will be trivial, will be G times the structure sheaf. And well, the other part of the question was, how about non-trivial stabilizers, right? Well, then we can construct many examples in the following way. If X is arithmetically Cohen-Macaulay, then we have this morphism right here, and we can resolve it by sums of line bundles, possibly in an infinite way. But if this resolution turns out to be finite and quite short, meaning the dimension of X minus 3, then it's a simple calculation that this foliation will satisfy these cohomological properties. And well, so we can actually construct many of them. That was all. Thank you.